Good. All right. Give yourself 2 points for that one. Okay. Guys, net force is what causes acceleration, right? But given the fact that you got multiple forces acting on you, like in this case, this guy is being pushed in this direction. The weight is pulling him down. There's a retarding force acting on him. Retarding force is not a force that turns you into a retard. It's just retarding your progress in this one. Okay, so when you have multiple forces acting on you, what's the meaning of a net force? Because net force is what causes acceleration. Real life cases like this one.
Chopping down a tree clean through by hand is a thing of the past. Pulling down a 30-foot evergreen with a tractor makes sense.
So the tractor pulls it this way. The roots will pull it in the opposite direction. The tree topples over.
But not with a 10-foot rope.
So when you have like multiple forces acting on a mass just like that, what's the meaning of a net force? What do we mean by it? Because we've been talking about net force nonstop for the past 2 weeks almost. This net force is what causes acceleration. So what's the net force if you got like two forces acting on a mass? Somebody pulling on this mass to the right, the other guy's pulling on the mass to the left. Forces are not the same, so it's an unbalanced system. So what's the meaning of a net force? Net force means the sum total of all forces acting on a system. It's the sum total of all forces acting on a system. Sum total, what does it mean? Does it mean that we add them up? Well, you add them up, it's going to give you 45 pounds. What good is that going to do? All right. Or is it more like the way you would think it should be, which is one person pulling on it this way, the other person is pulling on it in the opposite direction? So is it possible that the net force is 5 instead of 45? So all of a sudden, you notice that the direction matters. So we have to assign directions to it. All right. To the right, it's going to be positive. To the left, it's going to be negative. So the net force is the summation of all the forces acting on the system. This is sigma. That's the summation sign. Net force is the summation of all the forces acting on a system along the x direction. That's your x direction. That's your y direction. So net force is going to be responsible for the acceleration along the x direction. That's what it means. So you sum up the forces. F1 is going to be positive. F2 is going to be negative. Then the numbers is going to give you 5 pounds. That's it. All right. So meaning of the net force is literally you're summing up the forces. The direction is going to matter. So when you sum things up, positives, negatives, it could be subtractions, it could be additions, and so forth. That's it.
The dummy contorts and stretches from the immense force. In only seconds, its arm is wrenched off by one of the aircraft, while the other plane drags the broken torso down the runway. Stanley knows the same thing could happen to him, but he's determined not to back out.
Who'll make it?
I'm gonna make it.
Okay.
Like that?
It's time. The pilots gun the engines. The ropes pull tight as the two Cessnas try to take off at the same time, at the same speed, in opposite directions. Their tachometers have already risen to 1,500 revolutions per minute. Remember, the goal is 2,400. Stanley braces against the tremendous force. Now, at 2,000 RPMs, nearly enough to take off. Grimaces as he fights to hold his ground. Barbara watches, terrified and helpless. The tachometers now read 2,200, more than enough power to take off. Stanley has only 200 RPMs to go. Then suddenly, he's pulled off balance. It looks like he's being overpowered, but somehow he summons all his physical and mental strength to stop the two planes from tearing him apart. Both engines are now revving at a fierce 2,300 RPMs, more than enough for them to be climbing into the sky. And finally, 2,400. Stanley has done it.
Wow, good for Stanley. All right, guys, what's the net force acting on him right now? Use the chat. What's the net force acting on him? All right, so the net force acting on him is 0. How do you know that the net force acting on him is 0?
Because they're equal forces pulling in opposite directions.
Oh, okay, that's awesome. Okay, every single person who wrote something so far, give yourself 5 points. Give yourself 5 points for the explanation. That explanation, if this were a test question out of 2 points so far, you would say it's 0, and because the two equal forces in opposite directions, yeah, guys, that's an entire statement there is 1 point, no more than that. All right, and that's the sort of statement that is very questionable because it's more of an assumption that you're making. And I don't want any assumptions. I don't want anything that starts with I believe, I think, I feel. Net force acting on me 0 because complete that sentence and use physics. Don't use anything else. Make a factual statement. How do you know that the net force acting on me 0? You can't say that the forces are equal. You don't know that. You cannot feel the forces. You cannot see the forces. So that's not the way I would approach it. How do you know that the net force acting on me is 0? Okay, so this brings us to the next one. A lot of problem solving in physics is conceptual, guys. You resort to math when you want to prove points because you're trying to generate numbers. This is the sort of stuff that you do. You look at it, you say, wait a minute, what's the net force acting on this guy? It's 0, but how do I know that? What's the definition of a net force? You have to go back to the definition. Physics is all about definitions and formulas. The formulas are summary statements. of the facts of the situation in reality. All right, so what does a net force do? Net force causes acceleration. So this guy, is he accelerating? I'll get back to the definition of acceleration. Is he speeding up? No. Is he slowing down? No. Is he changing direction? No. So what's the net force? It's going to be zero because the acceleration is zero. I said nothing about the forces being equal. All right. Net force is zero. That's Newton's first law. So what happens when the net force is zero? The system is going to remain at rest. All right. The absence of a net external force, the first law says, the system retains its initial motion. All right. The object at rest is going to remain at rest. Object in motion is going to keep on moving in a straight line at a constant speed. This is an object at rest. The absence of a net external force is not an absence of a force. There are two forces acting on this guy. And these forces are so large that if I were to take his place, I would more than likely lose my arms. But the net force is zero, which means that the forces are in opposite directions and they add up to zero. They cancel each other out. When the forces cancel each other out, the canceling forces, it doesn't mean that there are no individual forces acting on the system. There are a tremendous amount of individual forces acting on the system.
Risen to 1,500.
There are no force acting on this guy now, of course. How do I know? Because he accelerated. He went from zero to something else. That's it. So that's what happens when one force is larger than the other one in this case. So it's going to end up moving in the direction of the resultant force, the net force. If this airplane applies a force, which is about a pound more than the other one, it's going to accelerate this way. Now, it creates a problem, obviously, because if they apply exactly the same force on this guy, what's going to happen is he can lose his balance. If he does, he can lose his arms, potentially lose his life.
Revolutions per minute. Remember.
Weight is the force of gravity acting on a mass. That's it. So the gravitational force acting on an object is known as weight. So here's Newton's apple. When you drop it, it accelerates because there's a force acting on it. That's it. So force causes this mass to accelerate, right? All right, so the acceleration is going to be the same as g under the influence of gravity. All right, so A turns into a g, so mass times the gravitational acceleration is known as weight. So the gravitational force acting on an object is known as weight. So the measure of gravity becomes weight. W is your weight, m is your mass, g is the acceleration due to gravity, and that's it. Okay, so get out of it. Weight is mass times the gravitational acceleration. Okay, what is g? What's the value for g? I want to do a bit of a demonstration. At the same time, I want to be able to see what you guys are saying. Okay, so acceleration is 10, right? It goes from 0 to 10. What am I saying? As soon as you let it go, it's going to start to accelerate. Okay, so it's accelerating at a rate of 10 meters per second squared. All right, so what is weight? Weight is mass times the gravitational acceleration, right? So does this mean that this thing has weight while it's accelerating at a rate of 10 meters per second squared? Because as soon as it hits my palm, it stops moving, right? There's no acceleration in this direction. Does this mean that it's weightless right now? Okay, the reason why I'm asking this question is because while it's accelerating, acceleration is 10. When it's falling, the acceleration is 10. 10 times the mass is its weight. Now it's not accelerating. So does this mean that it becomes weightless? It becomes weightless. All right, because the acceleration is 0. 0 times 1 is going to be 0. 0 times 100 is a 0. 0 times a trillion is a 0. 0 times cannon is 0. 0 times a ball is 0. So what's the acceleration? Acceleration is 0. So does this mean that it's weightless? Okay, so 0 times mass has to be 0. So does this mean that this thing is weightless? What's your acceleration right now? It's 0. What's my acceleration right now? It is 0. So does this mean that I'm weightless? So, I mean, the mass is still there, but what happens to the weight? That's what I'm getting at. So if you're thinking that this thing became weightless because it stopped accelerating, let me tell you something, guys. Yeah, it stopped accelerating, but I can feel its weight. Okay, just because something stops accelerating, does this mean that that thing becomes weightless?
Stephen adds some more weight. He's the world record holder in the hand and thigh lift. This day he's attempting 1,500 pounds, 6 times his body weight. He clears it easily. But ever the competitor, Stephen adds some more weight. A measly 10 pounds. A clean lift will now put him in the record books. Unfortunately, he'll break something other than the record. It's a gruesome sight as his leg crumbles beneath him. The weight is too much for his...
Well, just because the weight set is not accelerating does not mean that it's not weightless.
Body to bear.
It's got so much weight that it ended up...
The fibula and tibia bones in his right leg snap like twigs.
His leg snapped. Gotta tell you, this is disgusting.
Stephen learns a very...
All right, moving forward. So just because something stops accelerating, doesn't mean that it becomes weightless. The weight is still there, right? The weight is still there. This is not a commercial. All right, so it's still there, but there's no acceleration. So how do you account for it? Given the fact that this thing is not accelerating, how does it still have weight? Where do we get the weight from? All right, the weight is still there, but it stops accelerating because the net force acting on it is 0, right? The weight is pulling it in the downward direction, and the surface is applying a force on it in the opposite direction. This is known as the surface force. This is a reaction force. It comes about because this mass is pushing up against the surface with its weight. And so this is 90 degrees to the surface, so it's known as the normal force. Normal is not used in the sense of normal versus abnormal. It's just a mathematical term. All right, so this thing stopped falling because it hits the surface. The weight is still there. It's not going to vanish. That weight is the gravitational force that causes it to accelerate at a constant rate. It's there. That tendency is still there. The net force became zero because as soon as it hits the surface, there's going to be a reaction force acting on it from the surface. There's going to be a surface force. It's known as the normal force. It's called the normal force because normal means in mathematics, it means it's a force that's perpendicular to the surface. It's not used in the sense of normal versus abnormal. It's just that normal means it's a surface force. It's perpendicular to the surface. It's going to be a reaction force to any force acting against the surface. Any force applied to the surface. So it could be your weight could be the action force. Normal force is going to be a reaction force. You may be pushing up against some kind of a surface like a wall. Okay, so the reaction force is the surface force acting back on you. So the normal force is the reaction force in that case. All right, so if you are getting a reading from a scale, it's known as the apparent weight. That's a normal force reading from a scale that you're getting. So the acceleration becomes zero along the y direction. All right, so which means that the net force on the y direction is zero whenever a falling object hits the surface and comes to a stop. All right, so which means that we have to do a force summation on the y direction. So W is in the downward direction. Normal force is going to be in the upward direction. All right, up is going to be positive, down is going to be negative in terms of the forces. So N is going to be positive, W is going to be negative. All right, so the net force is what causes acceleration. You know the acceleration on the y direction is going to be zero. So which means that your normal force reading comes from your weight. It's going to be the same as your weight in essence. All right, so if you're standing on a scale, the reading that you get from a scale is going to be your weight or the apparent weight. Okay, given the fact that the scale reading is the same as your actual weight, why do we call it the apparent weight? Does this mean that the apparent weight, the scale reading, is going to be sensitive to the accuracy of the scale? I didn't say it right, so I'm just going to go back and restate it. Can you fool the scale into giving you a different reading other than your actual weight? That's what I'm getting at. It's called apparent weight because the apparent weight can be different from your actual weight. So case in point, let's assume that you're dieting. You want to lose about 10 pounds a week, and then you manage to lose about a pound. At the end of the week, you're standing on the top of a bathroom scale. It's 1 pound, guys. 1 pound. That's reasonable. Except you were a little bit too ambitious. That's 9 pounds. You wanted to lose 10 pounds. Obviously, you got 9 more pounds to go. And you decide that you're not going to leave that bathroom unless you lose 9 more pounds. Except you're in a hurry. You got to leave within the next 30 seconds. That's a mind twister right there. So how do you lose 9 more pounds within the next 30 seconds? What is it that you have to do? The only thing you have to do is just fool the scale, guys. How do you fool the scale into thinking that you lost like 10 pounds or 9 more pounds? What is it that you have to do? All right, so scale is what you're trying to fool. All right, so you're just trying to create the impression that you lost 10 pounds within the next 30 seconds. So how do you do that? Anyway, so before we get back to that question. All right, so downward force, upward force, they will be equal to each other. If the weight is larger than the surface force, obviously the surface is going to either break or it's going to crush.
Hello, sunshine. Sleepy, hey. Make room for shoes. The world's biggest shoe store is here. Nordstrom.
So you want to lose 10 pounds, 9 more pounds before leaving the bathroom, and you want to do it in the next 30 seconds. How do you do that? How do you fool the scale into thinking that you lost 9 more pounds?
Oh, 225. That means I lost weight.
Homer, you're on the towel rack.
What you need to do is display some of that weight onto something else. All right, guys, you can put 1 foot on the floor. Obviously, you're going to weigh less. Or you can put your arm on a countertop. You're going to weigh less. All right, so the apparent weight and the actual weight, they don't have to be the same. That's the reason why I'm on apparent weight. So the scale reading may not be the accurate measure of your actual weight. All right, what is it? The normal force is a force that's always equal to the weight of an object. Okay, most of you guys said B. For picking B, I'm going to give you guys 2 points. Victor, give yourself 5 points. It's a reaction force, guys. It doesn't have to be a weight. And it's not always equal to the weight of an object. It could be more than your actual weight. It could be less than your actual weight. It's just a reaction force to any force applied to your surface. All right, so A is the best answer. So those of you guys who pick A, give yourselves 5 points. Now imagine that you're inside an elevator, standing. Okay, you're inside an elevator. The elevator starts to go down. Do you feel heavier, lighter, or about the same? All right, so most of you guys are light sensitive, right? Light sensitive. Okay, and today's lecture is not working. I need to get coffee. Most of you guys are motion sensitive. That's what I meant to say. Everyone is light sensitive, so you can see in the light, but you guys are motion sensitive. Elevator starts to move in the downward direction. Do you feel heavier, lighter, or about the same? And most of you guys are gonna feel lighter, right? All right, is this just the feeling that you get? Or is this really what happens if you're standing on a scale? I mean, when you look down on the scale, the reading that you get from a scale, will that be smaller than your actual weight? All right, so I created a project done by one of the Chicago students, and he had done this project in a high-rise. He's standing on a scale inside an elevator. I'm not sure why he's not wearing his shoes. No, he's not naked, or else something else would be sticking out as well. This guy weighs 240 pounds, right? So look what happens. So what do we do? The elevator is going down. So it's just going to accelerate in the downward direction initially. And as soon as the elevator starts to accelerate in the downward direction, notice that its original weight is going to jump down, almost jump all the way down to 200 pounds. All right, so not only do you feel lighter when the elevator accelerates in the downward direction, evidently you do become lighter according to the scale. And then what happens is the elevator reaches a certain constant speed, and at that point you will feel normal. All right, so the elevator is moving at constant speed. Its actual weight is 240. Scale rating is 240. Everything is fine. Now the elevator is going to start to come to a stop. It's slowing down to a stop. It's just moving in the downward direction. All right, so would you feel lighter, heavier, or about the same? You know, you will feel heavier, right? All right, so according to the scale, as the elevators come to a stop while moving in the downward direction, you will feel heavier because according to the scale, your weight jumps up. I mean, his weight literally jumped up to 300 pounds. So we got three conclusions. No acceleration, no change in weight. When the acceleration is in the downward direction, you will feel lighter. When the acceleration is in the upward direction, you will feel heavier. So no acceleration, no change in weight. When the acceleration is in the downward direction, you will feel lighter. When the acceleration is in the upward direction, you will feel heavier. All right, so let's get back to the review. So fill in the gaps. So what's weight? Weight is the gravitational force acting on the mass, right? Force of gravity becomes weight, the measure of force of gravity. Measure of gravity, force of gravity acting on the mass becomes the weight of that object. So mass times the acceleration due to gravity is your weight. So how does weight differ from mass? Mass is the inertia, measure of inertia or measured inertia, and weight is the amount of gravity acting on that mass. So what's a normal force? It's a reaction force against any force acting on a surface. It's got to be 90 degrees to the surface, so that's the reason why it's known as normal. It's a mathematical term, and that's it. What's your apparent weight? It's a normal force reading from a scale. So does this mean that the apparent weight could be different from your actual weight? Absolutely. You can fool the scale. All right. You can shift some of your actual weight to a different surface, countertop the floor or whatnot. Also, it's going to be sensitive to the acceleration of the mass on top of it. So you're inside an elevator. Question number 21. It's accelerating in the downward direction. Do you feel heavier, lighter, about the same? So you will feel lighter, right? So that's the correct answer. When the elevator starts to move from rest in the upward direction, do you feel heavier, lighter, about the same? So you will feel heavier. When the elevator is moving at constant speed, do you feel heavier, lighter, about the same? So it's going to be about the same. All right, so. All right, now let's take a look at what happens inside the elevator. Let's set up the mathematics for it. So this is your center of mass, center of gravity, center of your balance. The force of gravity is acting on your center of balance. So which means that you got some weight. You're standing on top of a scale. Scale is right there. And here's the scale reading. All right, so that's your normal force reading, otherwise known as the apparent weight. Now, elevator can accelerate in the upward direction, positive acceleration, or the downward direction, negative acceleration, or it could be moving at a constant speed or standing still. So there's no acceleration. So let's come up with a mathematical model for the apparent weight. So I'm going to sum up. I'll do a force summation along the y direction. And is up, W is down. All right, acceleration could be up, positive. It could be down, negative, or no acceleration. So net force is what causes the acceleration. All right, so the apparent weight is what we're looking for. The apparent weight in this case is going to be the normal force, N, that we're looking for. All right, so this is our formula, M minus W plus M minus MA. All right, so add W to both sides. And that's it. That's the final equation. So your apparent weight is on the left-hand side. So how much you appear to weigh depends on the acceleration of this mass. If the acceleration is in the upward direction, you will weigh more. If the acceleration is in the downward direction, acceleration of your mass is going to get subtracted from your weight, so you're going to weigh less. All right, so there are three possibilities here, so let's just go over all three. One possibility is that the acceleration is in the opposite direction. So this is your actual weight. So the apparent weight is going to be acceleration of your mass larger than your actual weight. So your mass's acceleration is going to get added onto your actual weight. So that's the reading that you will get from a scale. When the acceleration is in the downward direction, your mass's acceleration is going to get subtracted from your weight. So you're going to weigh less according to the scale. Obviously, if there's no acceleration, your scale reading is going to be accurate to your weight. So your apparent and the actual weights are the same. All right, so that's the mathematical model. I'm going to turn this into a mind twister, a slight mind twister. All right, so this goes back to the observation that we had the first week. Remember the guy inside the elevator, the cable snap? Here's the guy, the cable snap. All right, what if this guy were also standing on top of a scale? And as soon as the cable snaps, what's the reading that this guy's going to get from the scale? All right, so that's what we're analyzing. So what is N? All right, so at this one, I'm going to open the room, floor for discussion. How much do you think that the person is going to appear to weigh according to the scale? What kind of a reading do you think this person is going to get from a scale as soon as the cable snaps? What do you guys think? So you're inside the elevator, standing on a scale, the cable snaps, you look down, what do you see? What's the reading from the scale at that point? All right, so I'm going to give 20 points for the best explanation. This is a mind twister. So what do you guys think? All right, I think everybody's minds are kind of twisted. You're not able to figure this out. All right, no one wants 20 points. All right, so you're inside the elevator. All right, so Jordan's scale reading would be the same as Jordan because the gravity is still moving you plus the scale. All right, Jordan, I'm going to give you 5 points for that one. At least one person says that the reading is going to be the same. All right, so moving forward, let's just analyze this. So what's happening is the cable snaps. You're inside the elevator. This is your center of mass. The weight is still the same. The weight is not going to change, guys. That's the amount of gravity acting on you, right? This is the amount of gravity acting on you. So that's not going to change. It's going to remain the same. So the question is the reading. So the question is the reading that you get from a scale. What happens to it? Reading that you get from a scale is going to be sensitive to the motion of the elevator, right? All right. So what's happening is acceleration is going to be in the downward direction. So let's grab the formula applicable to that case. So which means that the acceleration of your mass is going to get subtracted from your actual weight. That's what it means. As soon as the cable snaps, what happens? Your acceleration becomes the same as the gravitational acceleration. A becomes G. All right. So this A becomes G. So mg minus mg is going to be 0. All right. So your scale reading goes down to 0. All right. So what does that mean? What that means is your center mass is not going to move. You're going to be standing exactly where you're standing. You're still standing on top of the scale, except you're not in contact with the scale at that point. All right, because you're applying no force on the scale and the scale is applying no force back on you. You will feel weightless. That's what it means. All right, you're not going to be able to feel the floor under your feet. You're not going to move up. You're not going to go down. You will become suspended. You're going to move with the elevator at the same acceleration while feeling weightless. So that's what happens. All right, this is known as apparent weightlessness. You will appear weightless inside the elevator. You will feel weightless inside the elevator. So that's what happens when you reach. As soon as the cable snaps, you will feel weightless. Okay, so remember, there's a safety system that's gonna catch the elevator, and we'll bring the elevator to a complete stop. I can't even talk. I'm too tired. All right, very gentle stop is what we are dealing with. Okay, so if you have Six Flags there, I'm sure it's the same as the one that we got here in Chicago. So there's a giant drop. Just get in there. There's going to be an elevator. It literally goes into a free fall. And there's a safety system when it kicks in. You come to a complete stop without injuring yourself. So that's what should happen when the safety system kicks in. But this person had a broken neck. So the question is, how did they break his neck? So the investigation is going to continue. All right. So how much physics have we done within the past 10 minutes? I got news for you. None. Okay. So we made a few observations. We came up with a mathematical model that agreed with the observations. And we made it look like we were doing physics, but we didn't do any physics. How so? Guys, unless you can explain why this person feels lighter when the elevator is going down, starts to accelerate in the downward direction, it's not physics at that point. Yeah, it's related to physics, but you're not really getting to the core of the question. All right, so when the elevator starts to go down, you will feel lighter, right? So why? What's the reason for it? Don't tell me that the mass times your acceleration gets subtracted from your weight. That's not an explanation that I'm looking for, right? That's a mathematical explanation. It doesn't really touch the spirit of the question. It doesn't really answer the question. All right, so the reason why you're going to end up feeling lighter has everything to do with the reason why your body moves in the opposite direction of the acceleration of the car, right? The car accelerates in the forward direction, your body moves backward, right? Why? Because of inertia. You got mass. That mass is a tendency to retain its initial motion. That mass is a tendency to resist change in motion. Same thing happens here. Massive objects, they're not going to want to move if they're at rest. When the elevator starts to accelerate in the downward direction, mass, because it's got inertia, it's going to resist that change in motion. And that change in resistance is going to appear as the lack of weight in the scale. So there's going to be a deficiency in the scale that you're going to be seeing. All right, so the change in weight comes from your inertia. Elevator is moving at constant speed. What do you have a tendency to move in at constant speed. There's no change in weight. When the elevator is slowing down to a stop, your body wants to keep on moving at a constant speed in a straight line. So there's that tendency. So your body is going to resist change in motion. As a result, the tendency is going to appear as the extra weight on the scale. So it comes from inertia. All right, I see A again. Okay, very good. So the person weighs 170 pounds. Elevator is ascending, which means that it's going up. You know it's accelerating because it's got the units of acceleration. So acceleration is up, which means that you will weigh more, right? Very good. Give yourself 5 points. Okay, I see a lot of B's here, so let's analyze. So suppose you're in an elevator that's moving upward. It's moving upward at a constant speed, right? The velocity is constant. All right, so according to the scale, you weigh 600 newtons, so that's your actual weight. So you guys like B, so let's check to see if that's correct. So according to B, the scale registers a value. That's going to be equal to 600 newtons during the time when the elevator slows down to a stop. Okay, when the elevator is going up and slowing down, what happens? Guys, refer back to your own life experiences. Elevator is going up and slowing down. You will feel lighter, right? So you will feel lighter. So B is not the right answer. C is the best answer, if that's the case. Elevator is going up and slowing down. You will weigh less. That's what it is. All right, so either you know the answer because of your life experience or experiences, or you can figure out the answer from what little physics that we covered so far. All right, guys, the car is moving in the forward direction. You put the brakes on. What happens? Your body is going to move in the opposite direction of the motion, right? Of the vehicle. So your body always moves in the opposite direction of the motion of the vehicle. All right, so the car is moving forward, slowing down. Your body wants to move in the forward direction. Elevator is going up and slowing down. Your body's going to want to move in the upward direction. All right, remember, elevator is going up and slowing down, which means that the acceleration is in the opposite direction of the motion of the elevator, which means that the acceleration is going to be in the downward direction. When the acceleration points down, you will feel lighter. So C is the best answer. Those of you guys who got C, give yourselves 5 points. All right, so moving forward, when the elevator starts to move from rest in the downward direction, you will feel lighter because of inertia. When the elevator starts to move from rest in the upward direction, you will feel heavier because of inertia. And lastly, when the elevator starts to slow down to a stop while moving in the downward direction, so it's going down and it's slowing down, do you feel lighter, heavier, or about the same? So it's going down and slowing down. It's slowing down as it's slowing down. Do you feel lighter, heavier, or about the same? The answer to that question is going to be, all right, Javier, give yourself 2 points. You will feel heavier, right? It's going down and slowing down. Once again, life experience, or the motion is in the downward direction. Because it's slowing down, the acceleration is going to be in the opposite direction of the motion, in the upward direction. If the acceleration is up, your body wants to move in the opposite direction. If the acceleration is up, you will feel heavier. All right, so the inertia is going to make you feel heavier. All right, so we're done with that.